Hi, Kinesiology 3010. This is our Chapter 14 lecture, or Chapter 4 lecture on correlations. Here is our practice from our descriptive statistics section. So you had 10 variables that you were supposed to calculate. N, which is a sample size, the mode, median, mean, range, sum of squares, squared sum of values, the variance, and the standard deviation. Okay. You were also supposed to calculate the z-score and the t-score for these four variables, 2, 8, 3, and 10. Okay, here are the answers to that. So here are the answers you should have gotten for your mathematical computations. If you didn't get those answers, go back, try again, see where you may have missed something. If not, please reach out, and I'm happy to take the time and we can work through those problems together. Okay, the last one for our z-scores and t-scores, here are z's and t's for each of those individual variables. So hopefully you got these 8 answers also. If you have challenges with these, I'm happy to take the time and we can take a little bit more time practicing the mathematical computation behind these, because you do need to know how to calculate all of these variables for this class, right? Now let's just break into our section on correlation. Okay, correlation is a statistical test that is used to describe a relationship or an association between two different scores or two different variables. Okay, so it's really what happens to one variable as the other variable changes. And to do this, we use the Pearson product moment correlation coefficient, or the R value, which measures our strength and direction of the relationship. So how one score changes compared to another score within the same population, within the same group. This helps us understand the relationships between different variables, especially within our field. So the relationship between cardiovascular endurance and heart disease. So as endurance goes up, does heart disease risk go down? Relationship between obesity and cancer. As obesity goes up, does the risk of cancer go up? Strength and speed. As strength goes up, does speed go up or go down? And then the rate of feedback and learning skills. So we can use these in all different realms of kinesiology to determine how one variable changes when another variable changes. Okay, we can also use it to determine reliability and validity. So reliability is how repeatable a measurement is. And then validity is how well that one measurement is measures what we think it's measuring. So using, like, maybe for our VO2 max test compared to a 1 mile run test, how well does the 1 mile run correlate or relate to the specific VO2 max measurement if we use like a metabolic cart. So we can use this to determine reliability and validity, as well as how two different variables change. As one changes, how does the other change? So let's use an example. So we have our summer days, the temperature, and we want to know if temperature is related to or associated with water consumption while spending time outside. So when it's hotter, do we drink more water? Okay, so we have our participants going down. So we have seven variables, or seven different participants, the temperature that they were sitting outside in, and how much water they consumed. Okay, we're trying to determine, as temperature goes up and down, does water consumption also go up and down, also go up as temperature goes up, or does water consumption go down as temperature goes up? So we want to know the direction and then how well they relate to each other. So do they relate as one goes up 1 unit, does the other go up 1 unit? As one goes up 5, does the other go up 5? Things like that. So this is how we would look at it on a graph. We would use a scatter plot where we use one variable on one axis and the other variable on the other. And we're trying to see, as with each participant, so with participant who's out at 75 degrees and they consume 16, compared to the one that's 85 and they consume 20, and so on and so forth. And we're trying to see the relationship between the two or that linear path that they could create. Okay, we do this by using Pearson's correlation coefficient, or the R value. You remember from our lab 1 where we practiced our mathematical techniques, you had to calculate an R value. This is the same scenario. This measures the direction, so if it's a positive or negative, and the strength, how closely they're aligned. If we're using a linear association or a linear relationship between two paired variables. So they're paired within people when we measure them. So let's get more into that. So we have two different directions. We have positive and negative relationships. A positive relationship means that as the x variable goes up, the y variable goes up. Think of these as the two axes here. You can see them on your on the graph here. As one variable goes up, does the other variable also go up? Or as one variable goes down, does the other variable also go down? So a positive relationship, each variable moves in the same direction. So as one goes up, the other goes up. As one goes down, the other goes down. Okay. A negative relationship, or an inverse relationship, is where one variable goes up, the other variable goes down. Or as one variable goes down, the other variable goes up. This would be a negative relationship. As you see between the two, a positive relationship has a positive slope of the line. A negative relationship has a negative slope of the line. Okay, so here's an example of a positive relationship. Okay, as one variable increases, the other variable increases. And the same as one variable gets lower, the other variable gets lower. With a negative relationship, or an inverse relationship, as one variable goes up, so here as the x variable goes up, the y variable goes down. Or as the y variable goes up, the x variable goes down, or gets lower as one gets higher. So they're moving in opposite directions. Okay, if we have a low correlation or no correlation, there's no relationship between the two. So here our line of best fit would go kind of right through the middle. There'd be a zero relationship. So as one goes up, it does not mean that another will also go up, because here we have a high x and a low y. We also have a high x and a high y, and so on. So this is kind of a much more scattered and spread out distribution of our scores. So here we would say that there's no relationship between the two. So we can't predict what's going to happen on variable x from what happens on variable y. Okay, so that's how we get our direction. Our strength comes from our R value, which measures from -1 to +1. So if you calculate an R value that's not between -1 and +1, you did something wrong. The larger the R, the stronger the relationship. And by larger, I mean closer to 1. Okay, so in magnitude, closer to 1. So the closer it is to 1, the more perfect the relationship is. Okay, the lower the number closer to 0, the less relationship there is between the two variables. So if there's no relationship, is normally near 0. If it's a very close relationship, it's closer to 1. And then we'll get into the positive and negative determines the direction, and then the numerical value dictates the value, or the strength of that relationship. Okay, so this means that if we have a correlation coefficient of -0.5 and then another one that is of +0.5, they're at equal strength. So 0.5 is the strength of the relationship, how closely they're related. The negative and positive tells us if it's a negative relationship or a positive relationship. So think of them as two different pieces of information. So -0.5 is a negative relationship with a strength of 0.5. A positive 0.5 is a positive relationship with a strength of 0.5. Okay, so they would be in different directions but the same strength. So we can think of our R values in strength values and then as direction values. When we look at them in context, look at them when we're describing them, a strong association is above 0.7. A moderate relationship is between 0.3 and 0.7, and a weak relationship is below 0.3. Okay, so you can keep those in mind. So here are some examples. 0.9 would be a strong, 0.5 would be moderate, and 0.25 would be weak. Okay, this is how we give value or meaning to the strength of the relationship. So remember, it's above 0.7, strong. Between 0.7 and 0.3, moderate. Below 0.3, weak association or weak relationship. So now we're looking at these two. When we're looking at a stronger relationship, that line is of tighter fit, or more of the variables are lined up together. So here a strong positive relationship would have very close variables. So as one goes up, the other is also going up in a similar magnitude. With a moderate correlation, we have a more spread out line. So that line isn't as tight together, which means there's not as strong of a correlation, which means that as one goes up, the other goes up, but it may go up more or less depending on the person, because there is that variability between individuals. So now let's look into calculating it. Okay. These are based on linear relationships or straight line relationships. So going back here, we're looking at the straight line value between the two. Okay. There are some times when there may not be a straight relationship, or there may be a curved relationship. For this situation, okay, for a linear relationship, we're looking at a straight line. This is what Pearson product moment correlation coefficient tells us. In some cases, there's also curvilinear relationships where as one goes up, the other goes up until a point, and then they go down as one goes up. So this is kind of a negative and positive relationship. It's curvilinear, so it changes its shape throughout. This is not the type of relationship that we're assuming is there when we use a Pearson product moment correlation coefficient. If we used a Pearson correlation, it would probably say our line of best fit would be right through the middle, and that there would be zero relationship, when in fact there is a relationship, but just more in a curvilinear sense. We will not determine curvilinear relationships in this class mathematically, but I do want you to know that there can be linear and curvilinear relationships. Okay, so let's kind of go through some practice together. Okay, what's the relationship between ages of college students and the hours that they study? Just looking at this graph, okay, we can tell that if we drew a straight line through kind of the average of the points, we'd see that it would be going up with our slope, so that's positive, and those lines are pretty close, so I would say there's a strong relationship. If I look here and I see that I have a line of best fit and I know my R value, say I calculated it, and I found it's 0.79, that's greater than 0.7, so that would be a strong positive correlation between students' age and the hours at which they study. So younger students don't study as much, older students study more, probably by why they do better or worse in their classes. Okay, what kind of relationship is there between ages of college students and 100-meter dash? Okay, here we see that our line is still pretty close, but it's going in the opposite direction. We see it's going down. Okay, if I calculate my R value and it comes out to 0.78, but it's negative, that means I have a strong negative correlation. So as age goes up, 100-meter dash goes up or down. Okay, think about it. So as age gets higher, 100-meter dash gets lower. Okay, as age gets lower, 100-meter dash gets higher. So that means that older individuals run a faster 100-meter dash. So a negative correlation does not mean it's a bad relationship. Okay, that just tells us the direction that those variables are going. A better 100-meter dash time is a smaller time. So this tells us that older individuals in this population run a faster 100 meters. Younger individuals run a slower 100 meters. So it doesn't tell us how good or bad the relationship is. It tells us which direction those variables are going in relationship to each other. Okay, keep that in mind, keep that in mind. Okay. And then we can determine these relationships using our graphing technique. So looking at where they are on a scatter plot, we can then compute the R and determine the strength and the direction mathematically. But we'll often use both. We use both to describe it because we like to have a visual and a numerical piece of information. So what I want some practice for you to do, a graph using graph the relationships. You can kind of create your own little axis on your paper as you're going through this. I'm hoping that you can do some of these practice along with. So let's do a practice where we're taking body weight and we want to know what's the relationship between someone's body weight and chin-ups, or body weight and pull-ups, or chin-ups and pull-up scores. We'll start with our chin-ups and pull-ups. So we'll create a graph, create an axis for yourself, put chin-ups on the Y, put pull-ups on the X, and then put those variables together. So 10 and 8, 9 and 7, and so on and so forth. So pause, grab out your sheet of paper, create your own little scatter plot of these, and then when you're done with that, you can go forward within the lecture. Okay, here's what yours should look like. It should look somewhere like this, where we have a kind of a pretty close line between pull-ups and chin-ups. If we see that it's moving up, we know that it's a positive relationship, and it looks like it's probably pretty strong based on those two. And if we think about those two variables, if someone's able to perform more pull-ups, they're likely able to perform more pull-ups also, and vice versa, because they use similar muscle groups. So that's something we can think about it contextually. Now go back, and I want you to create another one where we use body weights and chin-ups, and create another one with body weight and pull-ups, now that you've had some practice. And see how those look compared to each other, or in relationship to each other. Okay, so if we look at this one with body weight and pull-ups, we see that it looks like our slope is moving a little bit more down. It looks like there's a negative relationship. And if we think about this contextually, pull-ups are a body weight movement. So as someone has more body weight, it will be more difficult for them to perform more of those body weight repetitions, because that relative weight that they're moving is much higher. So if we think about it contextually, it makes sense. Okay. Now here's an example of if we had a scatter plot with a 0 correlation, or an R of 0. So if we look at these, our line of best fit would probably move right through the center, which the slope of that line would be 0, or the R would be 0. That tells us that there's no relationship, so we can't predict or assume that as one variable goes up, the other will go up, or as one variable goes up, the other will go down. So we have very little information about how those two are related, and we can say that there is no relationship between variable X and variable Y.